that was a dumb time to start recording, was that decision to make a mole equal to 6.022 times 10 to the 23rd things, and having that atoms just bothers me, because it could be atoms or eggs or donuts or molecules. Yes?
If it's looking at just have 6.02, do you want us to add in the extra two?
Doesn't matter. This comes back to the same kind of thing as we did with Kelvin, 273 versus 273.15. I happen to memorize one extra digit. That's it. The reason we picked that number was that number allowed us to scale the atomic weights on the periodic table from being atomic now up to an actual measurement unit. Okay? So to give you an idea, we could do a quick walkthrough. If we look at carbon, the periodic table tells us that we have 12.01 atomic mass units. Okay, well, an atomic mass unit is this weird kind of meaningless number. Okay? It's not an actual measurement. So we could go through and look at the conversion between AMUs and kilograms. Okay? So we could convert AMUs up to kilograms. Okay? That conversion I'm not 100% sure on, but let's say it's 1.661 times 10 to the negative 24th kilograms is 1 AMU. Okay? So that's an insanely tiny mass. So if I tried to measure out a single atom of carbon, I can't do it. Okay? I literally don't have a balance to do that. So we said, well, let's scale up our reactions. Instead of looking at just a single atom, I'm going to look at enough atoms that when I go through to do this, I get a mass that's actually measurable for me. Okay? So what was, and it may not actually be kilograms, I think that's grams. What was the number that we decided to pick? Okay, well, the number we decided to pick had to do with kind of the other meaning on this. This was 12 AMUs. That's a mass unit per one atom. Okay, so if I calculate this out, this is now grams per one atom. Okay, so someone went through and said, well, that's not a measurable mass, so instead of looking at one atom, I'm going to look at a very large number of atoms, and I'm going to define that very large number to be a mole. And I'm going to define that number to be 6.022 times 10 to the 23rd. Okay? That now equals 1 mole. Okay? If I've done this right and memorized my numbers correctly, and because I haven't done this calculation in a little while, an interesting thing comes out of picking that particular number to represent a mole. Okay? I don't see anybody with a calculator. Oh, a couple people have a calculator. Let's run that calculation as shown. Let's see if I actually did it right. If you got a phone, you can use your phone. Enter that in, see what the number comes out to be. God, I hope I picked the number right. We'll find out very quickly if I picked the number right. I'm going to Google the proper conversion here. We'll even pause the video, there's no point. And according to our calculation, we get 12.01. Wait, what did we start with? 12.01. The reason we pick a mole is because that scales us up so that we're now at a measurable mass. Not only does it scale us up to a measurable mass, it allows us to use the number for mass on the periodic table directly out of the periodic table. I don't have to do some weird conversion. The atomic net mass now becomes a measurable mass, a decent unit system, grams, okay? But I had to scale it up, so it's no longer a mass per an atom, it's now the mass per mole. This is pretty cool. I've now got a unit system that matches all my measurement systems that we potentially have, at least within not significant, the SI system. Right? So that's pretty cool within the metric system.
Just to kind of like clarify the idea, you're saying it's like to give 6 eggs and then you just basically transfer it to 6 dozens, like, or the other way around.
Careful that. If we picked, let's just pick numbers actually match. 12 eggs, and now saying that's 1 dozen. Okay? So why did we pick a dozen to mean 12? Well, the argument that I've been making is why did we pick a dozen to mean 12? Why did we pick that as our number? Why not 13, 14, or 15?
Because we can only count to 12 as humans.
We can only count to 12 as humans because we get fingers, and then we only get a foot. Because we got shoes on, we can't count our toes. Okay, so we only get to 12. That's why we invented a dozen, was because our human brains couldn't deal with a number larger than that because I don't have the physical appendages to be able to count that high. So we invented a dozen. Okay? The same kind of thing is happening in science, except we can't count that low as far as grams. That's an unmeasurable amount. Okay? So what we did is we scaled it up so that that conversion between AMUs and grams disappears. We picked the number for a mole so that we don't have to do conversions. That's kind of cool. Right? That was nice. See? Chemists are cool. They made your life easier. Okay? We picked a number so that we don't have to do conversions anymore. This is also one of the reasons why I get less excited about a mole, okay? Because we picked a number so that we don't have to use it. That's what we did. So when chemists get all excited about it, well, I'm never going to use that number. It's just not going to happen. The only reason I'm going to be asked to use it is in a lecture class where I'm now forced to show those conversions. That's it. Okay? Which means you guys have to deal with it. Okay? But to a much lesser extent because I think it's dumb. Okay? Well, not really dumb. It's a very powerful thing. Okay? But the big part that we get out of this is that takes the atomic mass and that scales it up to now a normal mass, but a mass for mole. Okay? This is now the molar mass. So the periodic table uses or gives us molar masses. That's huge. Okay? That simplifies a lot of calculations. So if I now ask for the molar mass of carbon, all you have to do is look at the periodic table, and where it says atomic mass is now molar mass. Right? And that's using a unit system that we're used to dealing with. Right? What if I ask for the molar mass for water?
Take 2 hydrogens, 1 oxygen, add them together.
First step, we have to know that water is H2O. And we know hydrogen weighs 1 gram per mole, but there's 2 of them there, which means 2 grams per mole, and then I have 1 oxygen. So the molar mass for water becomes 18 grams per mole. Why not 3? What is the mass of oxygen?
Yeah, I just realized.
It's okay, so we have to be careful in our calculations.
I'm also very blind from the same
Okay.
here up here.
Well, let's make you test it. What is the molar mass for copper 2 nitrite? Okay, and actually, Greg's got something to tell us in the back if we all turn around. Oh, never mind. I thought he had something to say. What is the molar mass for copper 2 nitrite?
Is it Cooper or copper?
Copper. Why did this question become more difficult?
We have to first locate it and then understand what nitrite is.
Okay. While you were all turned around busy not looking at the screen, I very carefully erased the chemical formula. This question actually asks 2 things. You have to know your nomenclature to be able to come up with the chemical formula. Once you have the chemical formula, then you can look up and use the periodic table.
CuNa2 or something?
So awesome. Cu is copper. Okay? And then I heard an Na. That's a fantastic idea because you see nitrite begins with N and you'd be like, yes, it must begin with N.
NO.
So does N. So does Ni. So does Nb. Okay? There are too many things. So you can't just be like, oh, it begins with N. Oh, it must be Ni because it has Ni. So does nitrogen. So does niobium.
Nickel.
Okay? So does nickel. Okay? This goes all the way back to Unit 1. You have to be able to have these pieces. Okay? Officially, Unit 1 tells you nitrite isn't an element. So how would we do that?
Well, we're supposed to memorize.
We move into Unit 2, and in Unit 2, we aren't looking at just elements. We're talking about the polyatomic ions, and we would have to know the formula for nitrite according to our polyatomic ions, which happens to be NO2. What other hint tells us that maybe we're looking at a polyatomic ion and not just a single element?
The trifar nitrite.
Not quite.
The T.
The T. When you see a T, that's a really big tip-off. You're looking at a complex ion. Okay? None of the elements will use a T. What do they use instead?
A D.
They'll use a D. Okay? So nitrite. So would this be the proper formula?
No.
No, because
Charge.
we also have to know the charge. Nitrite is a -1. What is the charge on the copper?
2.
How do you know it's a 2?
Because it says it right next to the Roman numerals.
The Roman numerals. Is that formula balanced?
No.
How do we balance it?
You need 2 nitrites.
We need 2 nitrites.
That's a 22, so you'd have to do
Yeah,
a
parentheses.
parenthesis between the 2.
Okay?
Yay, we're smart.
All of that should be reflexive and be solved in probably under 10 seconds. Okay, we just spent a couple minutes doing that. So, what is the molar mass for copper 2 nitrite? Set it up. 63 plus 14 plus 16 doesn't equal 155. Two what? 2 of the nitrites, which means 2 nitrogens and then 2 oxygens. So, okay. Now if you add it all up, hopefully you get that 155. Do we get a second on that? Did you say 155?
Yeah, it's 155.57.
Grams per mole. We got a second? That make sense? Relatively simple calculation. You've got to use the periodic table to go through and add that up. Okay? Did we have to use Avogadro's number? No, so that was a boring calculation. Let's try it again.
Okay.
What is the mass in grams of 0.532 moles of copper 2 nitrite? Okay. Notice in the last question, we didn't have to do any fancy conversions or anything. We just added things up. That's cool. That's great. Okay. Theoretically, we could have added a whole bunch of extra conversions in that. Probably didn't want to do that, so we just kind of assumed those conversions were fine. All right. Do we have to do a conversion here?
Yes.
Yeah.
Why?
Because what we're given and what we need to find isn't or aren't the same.
Grams and moles. The measurement unit changed. This equals grams of our copper nitrite, and we're given moles of our copper nitrite. The substance is the same, the measurement unit is different, which means I have to do a conversion. In that conversion, what do I want to have happen?
You want to end with grams.
How do I make that happen?
Of grams in the numerator.
Why do I place it in the numerator?
Because it's what you're trying to solve for.
I'll partially accept that. It's not just that it's what I'm trying to solve for, it's that when I solve for it, where is it located?
Numerator.
In the numerator. So cool, I know that has to happen in blue. Do I know anything else has to happen?
Moles has to be in the denominator.
I would like moles to be in the denominator. Why?
So we can cancel out and get nothing but
So the units cancel out, and we would have a phenomenal answer. Cool. Is there a conversion factor between grams and moles provided in the question?
But we were supposed to memorize.
Kind of, sort of. They tell you that that the compound is copper 2 nitrite. You're supposed to know that that means that. You're supposed to know that the conversion between grams and moles for any compound is found in the molar mass. And where's that molar mass found?
The atomic mass unit.
In our periodic table. So we would have to determine the molar mass for copper 2 nitrite, which we literally just did. 155.57 grams per mole. Where's the 155 show up? Good. No, grams was the better answer. 155.57. What shows up with moles? 1. Now we can punch in the calculator and we run our calculation.
Oh my god, I should have that right.
Okay? So this becomes challenging. When we look at this, the given information was 0.532. So how the hell would you get this grams to mole conversion? Was that something you had memorized?
No.
No. What did you have memorized?
What the molar mass is compared to the atomic number?
How to find that conversion factor. That conversion factor was already embedded in the periodic table, but you had to know how to find it. Almost all of the conversions we're doing in this unit, you have to go out and find that conversion factor. It's not just given to you. You have to know where to find it. Okay? And a lot of that has to do with recognizing your units, measurement and substance. When the measurement unit changes, you have to do some kind of measurement conversion. Where do you find those conversions? If the substance changes, where do you find those substance conversions? Okay? So, new one. Do this one. Mass in grams, 2.55 times 10 to the 23rd atoms of lead.
Yeah.
Okay. So we're going to do a couple things here. We'll start with 2.55 times 10 to the 23rd over 1 times 207.2 over 1. Okay. How many people have numbers aligned like that in their calculation?
To an extent.
All I asked about is the numbers. Have those numbers multiplied by each other in their calculation? Okay, almost everybody. Okay, is that the right answer?
No.
No. Why is it not the right answer?
Because it gets you
Because
the longest number, and
No,
there's
it's
no,
not.
and there's no unit.
it's not even that. It's just the fact that it's not the right.
Is 4 times 4 equal 16?
Yes.
Yes. So that's right, isn't it? The answer is 16?
No, it's
No.
the units that are wrong.
Okay. You have to make sure that you're answering the question that's asked. Okay. In a standard, what's 4 times 4 equals 16? All you're focused on is the number. There is no measurement system associated with it. There's no unit system associated with it. So you can just punch that into a calculator and get a number. Okay. When we're looking at this kind of a solve or a question, what we need to do is not focus on the numbers. I cannot stress that enough. If you're writing numbers down when you go through and solve, you've done it wrong already. I don't care if you somehow lucked into the correct answer. You're wrong. Okay? And it's not because, well, I got the right number, so doesn't that make me right? No. And this is where we can run into debates. Well, the teacher didn't like my method. You don't have a method. You just threw stuff together and hoped it worked. That's not a method. Just because your number matches my number doesn't mean you're right. Okay? You just threw numbers together and magically achieved my response. Okay? If your magic fails you, you're wrong. And so what I'm trying to set up is not well, your calculation is wrong, but what was your process to get there? Because that process is what's going to dictate your long-term success. Okay? So, nothing about our process matches either of those two situations. Okay? Follow the process I'm asking you to do. What is step 1?
What you want to identify what you're showing.
What do I want? Grams of lead. Okay, and I saw a lot of people do that, and that's fantastic. That's good. Okay, that right there, okay, could potentially get you partial credit in a show your work. Okay, if you did that for all the show your work questions, you're not going to get partial credit for all of them, but you'll probably get partial credit because you've at least acknowledged that you've listened to me for the very first thing I told you to do. Okay, you do deserve some credit for that. Okay, what's the next step? Okay, so one option is going through and saying, well, in my calculation, I know I need grams of lead showing up in the numerator on the other side of the equation. Am I given the grams of lead in the question? Okay, so now we run into a potential dilemma on what do we start with. We know grams of lead eventually needs to show up, but I know nothing about that context. I would argue writing that in there is going to be misleading unless you have an idea on where to go with it. Okay, so one option, in a state of an almost vacuum, we should cling on to the only piece of given information we've got. Since there's only one clearly given piece of information, that's what we should start with. What were we given? No. Try again. What were we given? Atoms of lead. Okay? For those listening at home back over this, what was started to suggest was the number. The number is meaningless until we have a value, a unit associated with this. So this is atoms of lead was given to me. Okay? With that, I know I can put over 1 because it wasn't given with any other context, and I could now potentially put in the number 2.55 times 10 to the 23rd. Okay? This means I'm going to have to do a conversion. Why do I have to do a conversion?
Because we're trying to solve for grams of lead, not.
I want grams of lead, not atoms of lead. That statement in and of itself is a good statement, but I want to take it a step further. What part allows you to say that you need to do a conversion? I know, it's a hard question. Vague question.
You have atoms of lead in the numerator, whereas you should have grams of lead in the numerator.
Okay, and I would take a step back. Did the lead change? No. So the substance is the same. What changed? The measurement changed. I need a measurement conversion. The substance is going to stay the same through this whole process. I want to be able to convert atoms to grams. Okay, where I need that conversion. So I could go through and say here that I want atoms in the denominator because
You need to cancel.
I need it to cancel, and I want grams in the numerator. Does that conversion factor exist? A different question. Does that conversion factor exist?
Yes.
Where does that conversion factor exist?
Periodic table.
Okay. Carbon weighs 12 grams per atom. A single atom of carbon weighs 12 grams. When I go in, can I weigh a single atom of anything? No, why not?
It's
Too small. So does the periodic table give me grams to atoms? No. It does give me grams to moles. Okay? So what I'm acknowledging is that this conversion factor does not exist. So I need to do some other conversion. What other conversion do I want to do? Well, there's actually a couple options here. Okay? We could go grams to moles. I could also go atoms to moles. So I'm taking that information where I had grams and atoms, and I'm saying, well, which one do I want to deal with? Okay? A suggestion was leaning towards the periodic table. And if we lean towards the periodic table, we're keeping grams and we're changing atoms to moles. Okay? A suggestion prior to that was made a little bit quieter and with less support from the crowd was that we could do atoms to moles. Okay? Both of those are valid paths. Okay? But we have to acknowledge how we move through those. Okay? So which one do you want to look at? Okay? And because the audience, again, didn't support, we're going to go with the one that was not supported by the audience because, well, 6.022 times 10 to the 23rd atoms equals 1 mole, okay, which we're going to complain about because
There's no unit of measurement, so you have to add.
there's no unit of measurement?
Or I'm sorry, there's no
Substance.
Yeah, so you need atoms of that and moles of that.
Okay. What would happen in our calculation? Atoms of lead gets canceled. Awesome. I would now have moles of lead. Okay. Do I want moles of lead in my answer? No. What do I want in my answer?
Grams.
Okay. So I know moles of lead must disappear, and I want grams of lead 2 up here. Where is that conversion factor found? That's on the periodic table. So we have to be careful to make sure that when we use the periodic table, we do use it correctly. We're looking for PB for lead. 207.2 grams is 1 mole. Where did we find the conversion factor in purple?
Memorization.
That was memorized. That's Avogadro's number. Okay. But we didn't have to do that. We could have done instead dealing with our grams and moles. Okay, so if we go back up to the top one, what's the relationship between grams and moles? Where's that conversion factor found? Periodic table. The exact same place it was found in the bottom one, yes. Periodic table. 207.2 grams per 1 mole. Okay, what happens to our units? In that top case, nothing cancels. Oh my God, we must have failed. But don't panic. We at least brought in grams of lead. That's a good thing. Okay? So I'm going to have to do another conversion. In that other conversion, I want moles of lead to disappear, and what do I want also to disappear? Atoms of lead. Where's that conversion factor found?
Right below it.
Right below it, because we memorized it as 6.022 times 10 to the 23rd atoms is 1 mole. Depending on how you see the conversion, you run a slightly different calculation. Right? Remember how we started this whole argument? The suggestion was I take 2.55 times 10 to the 23rd times 207.2. And I got this really weird, massive number, 10 to the 23rd something. Number. I go, yeah, that didn't feel right. So number one, awesome. Your instincts kicked in and you're like, that didn't feel right. That's good. You should trust your instincts. Right? But your work there was so bare bones that you had no way to know why you did any of that calculation. Go through and look at our correct calculations. 207.2 times 255 times 10 to the 23rd. What did you do in your bare bones calculation? Oh, the exact same thing. Just you reversed it. Why did you do it? Why was that calculation done? Well, in your initial work, you had no idea, which means when you got an answer, you have no idea if that was the correct answer because you don't have any unit systems to support why you multiplied those numbers. In the two processes shown below, we now have reason to explain why we would do those conversions, why we would do the math that we're being told to do. Everything we're asking you to do is not to do the math. Okay? I could really care, I can't quite care less.
You can't.
I could care a little bit less, okay, on your ability to punch things into the calculator. Okay, because that is still part of your grade. You are responsible for being able to punch things into the calculator correctly. All right? But the majority of your points comes with the process. Okay? And this is sometimes why faculty don't like multiple choice. Well, somebody could randomly punch buttons into the calculator. Yeah. Okay? And the odds of you successfully punching things into the calculator are below 20%. Less than the odds of the multiple choice answer itself. Okay? So you have to know the process behind it. That's what you have to lock in on. So stick to that process. The instant you start varying away from the process, you'll get kind of yelled at from me. Yes?
So in mine, I have like all the same ones, like all the same like fractional stuff. They're just like in different spots. Would that get me marked off? Because I got
The
same answer.
placement, and so I want to address your question in two parts.
Okay.
I had all the same parts, but I got the same answer. Am I going to get marked off? Getting the same answer, yes, absolutely, I could mark you off. Okay? Because I don't care about the answer, I care about the work supporting it. Okay? Because what I hear there is, well, I took 2.55 times 10 to the 23rd, 207, times 207, and then I divided by 6.022. That gets me the same number. What I want to see is the unit work associated with it. If that unit work is there, you're fine. The sequence in which you organize that unit work, laterally, not up and down,
Yeah.
doesn't matter.
Okay, that's what I
Right.
was asking.
Because
It just happened in different places.
all of that comes from what you see and how you want to work it. Okay? How we solved this was, we've already made a change from how we typically solve it. Right? Because we started saying instead of doing big empty white space and right on the far left, we're now starting right next to the equals and working our way right to left. Okay? Because it's multiplication division, we can do that. We can
Yeah,
switch
it's
up
like
that
my
order.
numerator, like the one closest to like the grams of lead is the grams in the numerator and the molar.
Yep. And that's all fine. Okay? Kind of makes sense? Cool. Do it again.
Like, how do you get rid of the molar? Shit.
Okay, so let's go through and look at it.
One for however
I saw a lot of people jumping straight to the 64.07 grams of SO2 per 1 mole of SO2. That is a fantastic place to start because grams of SO2 shows up. That is what we want. Okay? You're not always given that. Where is that information typically found?
You're in a brain.
It's not in your brain.
That's on the periodic table.
It's on the periodic table. Okay, so in this case, we decided that wasn't a high value aspect of the question. What we wanted to see is could you do the conversion? So we gave you the molar mass. Sometimes you're given it, sometimes you aren't. It depends on what the question is targeting. So in this case, the question is targeting how you go through and solve. So grams of SO2, grams of SO2, fantastic. But I brought in moles of SO2. Do I want moles of SO2?
No,
So what has to happen?
you have to cancel it out and replace.
Moles of SO2 must show up in the numerator. So now the question is, am I given moles of SO2? No, I'm given molecules of SO2, so that doesn't work. Okay? So I'm going to have to convert the moles of SO2 into something. This is where I get a lot of people saying, well, but I've got grams of SO2. Fantastic, awesome, do it. Grams of SO2, 1 mole, 64.07, and what did you just do?
You cancel both of them.
You just undid all of the work you've done. Gone, deleted. You're fine to do that, just realize you're starting over. And in starting over, what's the first thing you'll do?
Same thing.
Okay? So that conversion factor, while a valid conversion factor, is not a useful one. When we're bringing in conversion factors, it's not I have one, so I'm going to do it. Okay? If I ask you to convert minutes to days, which way do you go? Minutes into seconds or minutes into hours? Minutes into hours. You did that really fast. Why'd you not go minutes into seconds?
We know better.
Because we know seconds is slow.
The same thing is happening here. You have to choose the proper conversion system for what you're trying to do. Minutes up to days, I need to be getting closer to days, not further from days. You have to think about the conversion factor you're using, not just throwing one in. Okay? That is much more challenging because you have to know that. Okay? You have to have that process built in. Okay? So what do I want to convert moles of SO2 to? Okay? One of the suggestions that I'll get is atoms. Okay? And ultimately atoms of SO2. There's an it. What's your it on that?
I don't know. I don't really like doing atoms because it seems like a little bit of extra work involved.
It's the fact that we don't even have atoms to
Yeah.
begin with.
We don't have atoms. It's sulfur dioxide. An atom would be sulfur. An atom would be an oxygen atom. We don't have an atom. What do we have? We have a molecule. It's a molecule of SO2.
Even tells you one molecule.
Okay? So it's not atoms, it's molecules. I know why you want to go to atoms, and that is entirely my fault as far as the slides go, and I don't know if the textbook effed it up as well. But when we look at our conversion factor between moles into something else, on the previous slide it says 1 mole equals 6.022 times 10 to the 23rd atoms. Okay? And you've focused on that, and that's good. You've got that information. And yet what happens every time that slide pops up?
You erase atoms.
I erase atoms. So you've hyper-focused on that information, but you're not also hyper-focusing on the fact that I'm deleting the word atoms. Okay? That's an important thing to distinguish there. A mole is any number of things. If you go to the store and buy a dozen, what did you buy?
Doesn't work.
A dozen what? You have to have the thing associated with it. Okay? In chemistry, what are our things? Atoms.
Grams.
That's a measurement, not a thing. Molecules. Those are our things, atom and molecules. So either of those two units can be used for Avogadro's number. Okay? So do I have a conversion between molecules and moles? That is Avogadro's number. Okay? Wait a minute. Everybody's going, yeah, see, I told you so. Okay, let's rewrite this into something that's a little bit better. Dozen eggs. 12 dozen eggs is 1 egg.
So it was right.
Wait, what? That's not true. I know that's not true. 6.022 times 10 to the 23rd goes with the molecules. It's the things.
I'm gonna cry.
Oh, how the money is falling from.
Okay? Some of this can come from trying to memorize where those numbers are tied to and what units attach to them. You have to get those down. Okay? This is that big all-encompassing conversion factor you have to know. Okay? You have to memorize what those numbers are tied to. You have to. Okay? This one becomes harder because what do you memorize the 6.022 times 10 to the 23rd or tied to? Can you tie it to molecules?
Apparently so.
We can, yeah.
No, why not? Because molecules could be atoms. It could be planets. It could be stars. It could be eggs. It could be donuts. Tying the 6.022 times 23rd to the molecules doesn't work because molecules can be anything. So that number doesn't match. What you could do is tie 1 to moles, and then your 6.022 times 10 to the 23rd is any other thing. To James's suggestion earlier, is a gram a thing? No, a gram is a measurement. Okay? So we have to be careful that our measurement units don't slide into this. These have to be physical objects. Okay? What happens? Moles of SO2 cancel. I'd have grams of SO2. What do I want? Grams of SO2 per molecules of SO2. Is that my answer?
No.
No.
Get rid of molecules.
Officially, I need to get rid of molecules of SO2. Am I given molecules of SO2? I'm given 1 molecule of SO2. The units of molecules of SO2 cancel. Now I can enter it into the calculator and I get my final answer. So good job. Yes, sir.
Because you're not, or it's not tied with anything, do you have to throw a denominator and a 1 underneath it, or can you leave it as just the 1 molecule of SO2?
It's up to you. Based on how we've been doing it in the past, it can be helpful to show that denominator always with the 1.
Okay.
I'm suggesting that as something helpful for you to do. I have to break my training where I don't do that, and I'm still fighting that. So you're right. I should be showing that fraction there with the 1 underneath to emphasize the fact that that's given information in the numerator.
But
If you don't show it, it doesn't have any effect. Okay? It's really just a placeholder.
More
So-
people have to know that that is a
Numerator.
quote unquote numerator.
Yeah. So if I asked you, let's try this again. What did I just write?
0.12.
Okay, I tried to make that dot really tiny, but the pen has gotten better in technology.
I didn't see it until I pointed it out.
Cool! Somebody didn't see it. So what could we do to make sure that that comes in very clearly as 0.12 and not 12?
Blacken that dot.
If you put a 0 in front, why would you write 012? That doesn't make any... Oh, there's a decimal point. That leading 0 is not a requirement. It's an aid for you to emphasize the fact there's probably a decimal point and you just didn't punch your pencil hard enough. Just like the fraction with the 1 underneath. Same idea. Okay? Make sense? Awesome. Okay. We're not going to do that one because we need to advance a little bit more. I would highly encourage you to do that one on your own and confirm it with me. Okay? So we'll just...
This particular problem, he's had people spend a lot of time on them in the past, and it is a clear indicator of who knows how to do this stuff and who doesn't.
Yeah.
There are about 5 steps if I remember correctly.
I think it's only 3 or 4. I think it may just be 3. We'll call 4. Okay. Call it 4. So if you want to take a minute to write it down so that you can go home and practice it. Okay. This is a really important question for you to prove your abilities on. I won't say it is on the next test, but there's probably a high probability. And I am fascinated by technology. I put stuff up like the Lewis structure rules, and everybody, instead of writing out the rules, pulls out a camera. I asked you to go through and write this one down. What do? You all write it down as opposed to like pulling out a camera and just taking a picture of it. Seriously? Next time I'm going to tell everybody to write down the Lewis structure rules and see if people actually write them down then, as opposed to just taking out a camera. You guys got it?
In this instance, they are listening and following directions.
Oh, they're following directions, yeah. We good? Okay. So, Chapter 9. Chapter 9 is taking everything that we've learned throughout the whole semester, including Chapter 8, and it now applies the chemical equation to it. Okay? Chemical equations are cool because what do they allow us to do?
Get more stuff wrong.
Work out the problem.
What can I do with a chemical equation?
Ooh, similes.
I don't know. There's just nothing you can do with a chemical equation.
Equation is like a box of chocolate.
You can create new elements.
Also, what's the chord on calories?
I can create new elements.
Well, not create new elements, but
What am I creating?
you can.
Compound.
I'm creating compounds. Okay? A chemical equation is a recipe. Okay? It explains to me how I can make something else.
I got this.
What is this doing? I'm giving grams and how I can make it into milliliters. That we call the conversion factor. We've dealt with those a whole bunch. Guess what a chemical equation is?
Conversion factor.
It gives us a conversion factor. We just have to be able to pull the information out of that format. Okay? Same thing as a bicycle. Simple instructions to build a bicycle. What do I need?
Wheels and a frame and tire.
Okay? I need 2 wheels in a frame. That looks kind of complex. Could I simplify it?
Probably.
Yeah, to what?
Wheel times 2 or times 3.
2 times wheel. That's still kind of complicated. How could I simplify that?
One frame. Or
That doesn't make a bicycle.
why?
You mean like a chemical equation? Yes, exactly like a chemical equation. Okay? When you're asked to build something, you got the Lego instructions or whatever, or an IKEA piece of furniture. That's a chemical equation. Okay? Identical to it. One of the problems with a chemical equation, though, has to do with scale. In a chemical equation, your pieces are so small that you can't see them. When you go through to build a bicycle, can you see the wheel?
Help.
Yes.
Yeah, you can manipulate it. You've got that kind of secondary context to be able to manipulate and deal with that system. Chemical equations don't do that. So how do chemical equations fix that issue? Because if it's so small that I can't actually manipulate them, how would I use a chemical equation? What do we do? How do I do chemistry? Do I work on the atomic level?
Yes.
No.
No,
We literally just had a unit, chapter 8, talking about what we do.
you scale it.
We scale it up to a mole of things. Okay? Now we can work with it on that level. If we think about building a bicycle, how many of you have ever worried about building 50 million bicycles? You haven't. That scale is now too large for our human brains to deal with. So even when we look at the chemical equation or the process for building a bicycle, we still boil it down to 2 wheels plus a frame equals a bicycle. And we just scale it upwards. Okay? Is scaling things upwards kind of a big deal?
Yes.
Yes, it is such a big deal that what happens to most businesses when they scale upwards? They fail miserably at it. Okay? So chemistry is taking something so small and scales it up to make it more reasonable to deal with. That more reasonable thing to deal with, if we compare it back out to our real world situation, is so unsuccessful that companies fail when they do that.
Why do they do it?
Okay? Why do we do it? Because it allows us a basic understanding of how things work. Why do companies scale upwards? If your job is to just make bicycles and you only make one bicycle, are you going to have a decent living?
No.
Probably not. Do you need to scale upwards?
Yeah.
Yes. Why do companies scale upwards?
Profit.
They're trying to get some profit so that they can make a decent living. Right? So we have to deal with those. Okay? We have to deal with that scale system. Okay, so let's go through. We've got this basic pattern down. Someone built 4 bikes. How many wheels and frames were used? How many wheels were used?
8.
How many frames?
4.
You did that awfully fast. How'd you do that?
Simple math.
Because of what you had.
Simple math is the most common answer to that question, and I would argue no, it's not simple math. It was an algorithm that you punched through in your head. What was the algorithm that you punched through in your head?
4 times 2.
Whoops.
Yeah.
What am I solving for?
You're so
Wheels, given how many what? 4 bikes. How do I convert bikes into wheels?
complicated.
2 wheels equals 1 bike. And you're competent. No, not at freaking all. What we're doing is making it explicit what you're doing in your head. Why do we need to make it explicit? Turn it into chemicals. And now you're like, oh, that's too hard. If this is easy for you, so is chemistry. What you're doing is putting a mental block on it and saying, well, that chemistry stuff is hard. That's your fault, not mine. Okay? You have to acknowledge this is exactly what you're doing. Nothing about this is different than what we're doing in chemistry. Literally nothing. Okay? The part that's difficult for you is you're trying to extrapolate to things that you don't physically use. The process is identical. If you don't have a process, guess what happens? Right? It falls apart. You put your underwear on your head. Okay? For those of you like, well, that's not a process. I'm pretty sure that's a process. You have a process for putting on your underwear. And I'm pretty sure it doesn't involve going over the top of your head. Okay? You've internalized that process, and that's cool. Okay? What I want you to do is stop internalizing it so you can apply that process to everything else. Why do you need to apply it to everything else? Because that's life. If you can't apply your knowledge to other situations, that knowledge is completely and utterly useless. Okay? When we talk about writing, we're talking about how you apply that writing into a different circumstance. Why? Because when you leave this class, are you going to be writing to Greg for the rest of your life? No. And by writing to Greg, you can write emails to Greg. That's nice. You should do that. Okay? But you're not going to be writing up a report to give at your job and be sending that letter to Greg, being like, hey, Greg, here, I did this. No, it doesn't work. Yeah, exactly right. Okay? In fact, I believe that violates some laws.
Yeah. Just a smidge.
Just a
Okay?
couple.
So what we have to be able to do is to apply that knowledge out to that different circumstance. That's what we're trying to give you, both on the English side and the chemistry side. We're giving you those skills to apply outwards. Okay? 6 wheels and 3 frames. How many bikes can be made?
2, 1,
Three
no,
bikes,
2.
3 bikes.
2, 3,
Actually 3.
3. I should stop listening to your math. We get 3.
Shouting out numbers.
Okay? 6 wheels. Okay? 2 wheels make a bike, so I can divide by 2 and I get my number. Okay? 3 frames, 1 frame equals 1 bike. I'm doing my conversion to get 3 bikes. Since the numbers are the same, we get 3. What if I give you just 2 wheels? How many bikes can be made? You'd say none because there's no frames. Good. That's a phenomenal reading of this. Unfortunately, chemistry doesn't read that way. Chemistry, and I admit that I'm guilty of this and I do try to fix it. Right? Chemistry reads this as given just 2 wheels and an excess of frames. It doesn't say that, but we mean it. How many bikes can be made?
1.
No,
1.
it drives me nuts, just for the record. It drives me crazy. It's
Right.
not explicit, it needs to be explicit. There's something
It should
wrong with it.
absolutely be explicit. Part of this class has helped me as an educator reframe questions to try and make sure they're explicit. Okay? That doesn't mean you'll see that everywhere. So watch out for that. Minimally, you should be like, this isn't explicit. Do you actually mean that? Okay, you should ask. Because what happens if you don't ask?
You failed.
We assume.
You assume. So if you assume that they mean it, but then the teacher says, well, I didn't say it, you're screwed. If you assume that they didn't mean it, but the teacher does assume, you're screwed. So you need to ask on those questionable situations.
The question is flawed.
Right? Yes. 3 wheels, 2 frames. How many bikes can be made?
1.
How'd you get 1?
Because there's 3 wheels and you need 2 wheels per bike.
But if I look at 3 wheels, and I know I'm setting this up horribly, but I'm doing it this way anyway.
Bike and a unicycle. There you go. I'm just saying.
Wheels, bike, 1 bike, 2 wheels. Doesn't this equal 1.5 bikes? Can I build half a bike?
No.
A unicycle.
In chemistry, probably.
Why in chemistry is that? Yes, probably. Can I build half a bike?
Because chemistry don't give no crap about rules.
Nope. Chemistry actually has a very valid supporting rule behind why we can do 1.5. In chemistry, are we only using a single molecule?
No.
What are we using? A mole. And what is a mole? Many molecules, a lot of molecules, 1,000. This says 1.5 bikes. If this said 1.5 moles, can I have half of a mole?
Yes.
Yes. So in chemistry, those fractional values are absolutely acceptable, right? Because we aren't doing single unit conversions, we're doing mass amounts. Okay? So that whole fractional thing that you guys did, oh, you can only make 1 bike, not 2 bikes, or not 1.5 bikes, because you can't have half a bike. That was fantastic in your math class when you dealt with small systems. We're not a small system. Okay? We're a very massive system, and at that massive system scale, we have to be able to recognize that we can have half values. Okay? So last one, 40 grams of wheels, 15 pounds of frames. How many bikes can be made?
Depends.
What do you mean, no idea? Everybody else answered all the other ones. Why are you telling me no now?
We don't know how much each wheel weighs or how much a frame weighs.
Okay? I always find this shocking. We go through and do these examples and people are spot on. We get to this last one, oh, yep, can't do that. I don't know how much those things weigh. That's because that equation to build a bicycle, what is the unit system?
Wheels and
It's the counting unit system. It's the number of pieces in that representation. That representation is identical to a chemical equation. And because it is identical, when we use a chemical equation, the measurement system that we're using is the number of pieces, not the number of grams. Why does that become challenging? When you go into the lab, what do you measure out? Do you measure out the number of pieces?
no, we measure out in grams.
You'd measure out the grams. So if we're going to use a chemical equation to convert one substance to another, what am I going to have to do to that gram? I'm going to have to convert that into a counting unit. What is my counting unit in chemistry? Cute furry little animal, the pony noise. Nobody's seen a cute little furry animal with a pony nose? A mole! Thank you.
What? They're not
I'm going to have to convert it to moles. Once I'm in moles, now I can deal with my chemical equation. Just like with these grams, once I've converted the grams of wheels into a number of wheels, the counting of wheels, I can use my chemical equation. I can use that conversion system. Okay? So when we go through and look at a chemical equation, this thing scales out a bunch of stuff. But the way we first looked at our chemical equation was 2 molecules of nitrogen oxide. 1 molecule of oxygen produces 2 molecules of nitrogen dioxide. That's how we talked about it initially. Okay? And what we're saying that we've now advanced far enough through our chemistry that we can't use that system anymore. And we can't use that system because I need to go into the lab to start making these measurements. I can't measure 2 molecules. Okay? So 2,000 molecules. Well, if it's 2,000 molecules, all we're doing is scaling everything up. What are we scaling it by? To get that 1,000 molecules, what did I do? If I said 2,000 molecules here, 2,000 molecules of what? I know where you're going with that. It's a nice try. Just nitrogen oxide. I want molecules of what? 1,000 is 1,000 molecules of O2. How do I convert molecules of NO to molecules of O2?
We just take, because isn't
Yes. Vocalize it. Keep going.
oxygen half of the equation of
I don't quite accept that one. Where do I find, so you're saying a half. So really what you're saying is I should be placing a 1 here and a 2 here. Where did you get those numbers from? Where did those numbers come from?
Like that's really just considering the oxygen.
So we're saying, where did the number in front of O2 come from? Where did the number in front of O2 come from?
Number of molecules of each substance.
Where did the number in front of NO come from?
The amount of the compound.
The equation.
From the chemical equation. And in particular, the balanced chemical equation. The coefficients in front of the species from the balanced chemical equation. That's where the numbers come from. To convert substances, we need the coefficients from our balanced chemical equation. That's why we have a chemical equation. So as you were stumbling all over this, you literally just aced it when we looked at bicycles. It's the exact same thing. Literally no difference. You're like, well, I can't figure it out now. There's that block. Chemistry, physical world. Oh, those can't be true. No, they are the same thing. Okay? And that's hard because we have to break that barrier. I have to convince you that that barrier shouldn't exist. Okay? And that's not easy. Okay? That's why I have to stand in front of you to talk to you about this. Okay? We could scale it up by thousands. That unfortunately doesn't get it big enough. So what do we scale it up by? We scale it up by Avogadro's number. Do I really want to write 12.04 times 10 to the 23rd in that? No, God, that would be awful to have to write that kind of number in front of all of my coefficients. Okay? But I picked that scale up because that can now convert into 2 moles. 2 because
2 times Avogadro's number.
it's the coefficient from our balanced chemical equation. And as long as I scale everything up by the exact same amount, Avogadro's number, I can now just say 2 times moles. What was a mole? 6.022 times 10 to the 23rd. What is 2 times 6.022 times 10 to the 23rd? 12.04 times 10 to the 23rd. This is an amazingly lovely system that establishes this. What becomes kind of crazy out of this is that we can now do these conversions, okay? And we can set this up. The big deal, this single equation gets me 6 conversion factors. On average, a single equation probably gets you close to 7 or 8 conversion factors. Which one of those conversion factors should you use? Why are you saying the first one?
Well, it says since 1 mole of NO2.
What are you reading to decide that you should use the first one? Yes, I like where you're going. I think you're wrong, but I like where you're going.
Bullet point. The one bullet point. There you go.
We're looking at the question. We're using the question to tell us what conversion factor. We're using the question to provide us the context to allow us to provide the information to answer the question. Okay? That's the point of those conversion factors. You have to know that that information is there. Once you know it's there, you set up your equation and you look at the substances. Did the substance change? Well, where do I find how to convert substances? That's a good question. We're well beyond time, so we'll have to stop there.